Welcome this morning. Before we get started, first of all, I got some questions. Kenley, did you have anything that you wanted to discuss before we start? Okay, great. Well, thanks everybody for coming this morning to Max Fagan's defense presentation. We'll be talking about some of the work he's been doing in supersonic retropropulsion flight optimization. Max has been a very, I would say, a strong Mars enthusiast. He's interned at a lot of places, including NASA Ames, Made in Space, and SpaceX, in his quest to go to Mars. He's also been featured in a popular science article. I forget what month that was, but I thought that was pretty interesting since he didn't tell me and I got my copy and started, I was like, I know that guy. As you'll see, he's very enthusiastic about Mars and trying to get people there, which is the topic of his presentation this morning. So with that, go ahead.
Okay, thanks, Professor Wren. Good morning. Thank you all for coming by. Like Professor Wren said, my name is Max, and the topic that I'm going to be covering today is a technique for landing humans on Mars, specifically larger spacecraft that are capable of carrying humans, and the challenges that are present in trying to overcome some of the roadblocks that are in the way of making this method a practical reality. So just a quick review of the history of Mars EDL and why we were focused on this problem. We've been flying to Mars since the 1960s. 13 spacecraft have managed to make it to the top of the atmosphere that were supposed to make it to the top of the atmosphere. And of those, 5 of them were destroyed, or 4 were destroyed before they were able to make it to the surface. So this is statistically as bad of a record as launch vehicles had in that era in getting to Mars. So from a statistical perspective, launching to Mars is just as dangerous as trying to land on Mars. And it is not something which we have necessarily got a proper handle on as to the reason why every single one of them failed. The loss of Polar Lander is still somewhat of a mystery. Beagle is still somewhat of a mystery. So we still have a lot to learn in terms of what's required to get spacecraft to the planet Mars. Certainly more before we can start sending people with any reliability. Obviously, this is an unacceptable track record if you want to send people. And part of the reason why it's so difficult is because the loads are very, the loads and conditions that a spacecraft experiences in EDL are very widely spaced. There's a very large range of design parameters you have to design the system to accommodate. A typical way to think about it is to break it into 2 phases. A high energy phase, which takes place from entry interface when the vehicle arrives from orbit, and stops somewhere around the Mach 2 region. It can sometimes go down to Mach 1.5, depending on what feature you're talking about. But generally, you can divide it into 2 phases, partitioned by Mach 2. In terms of altitude, the second phase doesn't really start until you get close enough to the surface to engage in practical terrain guidance. That's about 10 kilometers, depending on the method that you're employing. So breaking it into these 2 phases lets us kind of separate the two major design challenges, as I hope you'll see. We're going to be focusing today mostly on the high energy phase. A lot of the developments that you hear about EDL, the novel stuff, the real breakthroughs in the last 30 years have taken place mainly in the terminal phase. And they're very valuable breakthroughs, but they don't really help solve the problems that we're after. So to get an overview of the difference between the 2 phases, if looking at the trajectories in energy space, so altitude, velocity space, we have to take the vehicle from entry interface down to a touchdown point at some non-zero but very low velocity. And the most critical parameter that defines the way a trajectory responds in this space is the ballistic coefficient, which is the mass of the vehicle divided by the drag coefficient, typically the hypersonic drag coefficient because that's typically a constant, divided by the aerodynamic area. So for a vehicle with a reasonably low ballistic coefficient, like 50 kilograms per square meter or so, the trajectory will look something like this. It'll fall from space until the atmosphere gets thick enough to cause deceleration. It'll lose velocity very fast over a very short altitude range before it'll reach terminal velocity and then impact the ground at whatever terminal velocity is specified by the ballistic coefficient. If you increase the ballistic coefficient, the vehicle will penetrate deeper into the atmosphere before it levels out and then comes to a stop at a higher velocity. So a higher ballistic coefficient means a higher terminal velocity. Now, 50 to 100, these are considered reasonably low ballistic coefficients. These are not something that a human-sized spacecraft would typically assume. A human-sized spacecraft, 200, 300, 400 range, that if you simply fly ballistically, this is what happens. The vehicle never reaches its terminal velocity. It's still accelerating when it hits the ground. I'm sorry, in this case, a ballistic coefficient is not a ballistic coefficient of 200 is decelerating by the time it hits the ground, but it's still going at Mach 5, Mach 6, which is obviously unacceptable. So if we take a look at the vehicles that have successfully flown to Mars, take a look at their ballistic coefficients, you can see they all fall in a pretty narrow range from 60 to 90 or so, with the exception of the Mars Science Laboratory, which is the current record holder of 135 kilograms per square meter. But even in that case, that's still a pretty narrow range. That's nowhere near the 300, 400, 500 that we have to accomplish in order to land a human-rated spacecraft. You can also see that the velocity at which the parachute has popped out, which is typically the transition between the high-energy phase and the terminal guidance phase, is all within the same range, Mach 1.5 to Mach 2 or so, with the exception of Viking 1 and 2. So keeping those factors in mind, let's look at their actual trajectory in energy space here. So this is every trajectory of every successful lander that has ever made it to the surface of Mars, with the numbers indicating the ballistic coefficients in kilograms per square meter. So the velocity at entry interface, this range right here, is defined by your transfer window. There's not much you can do about that. It's pretty much specified by the amount of time it takes to get to Mars in your launch window. However, you'll notice that the vehicles that have larger ballistic coefficients, like the Mars exploration rovers and Curiosity, if you compare these two, they started with roughly the same entry interface velocity, but Curiosity penetrated much, much deeper into the atmosphere before it decelerated the way the Mars exploration rovers or the Vikings did. Now, what would happen if we were to fly something like the Apollo capsule in a situation like this? What if we took the Apollo capsule, started it with the same entry interface conditions, same flight path angle, and same velocity as Curiosity? What would happen? Well, it turns out this is what would happen. So this is about Mach 3, Mach 4, Mach 5 or so, is the impact velocity. So that kind of puts a handle on the size of the problem we have if we want to put a human-rated spacecraft on Mars. Because Apollo is not a very big spacecraft. It's not something you'd be comfortable flying all the way from Earth in. And we say, well, what about all of this? What about all these technologies? What about the sky crane? What about the airbags? What about the enormous parachutes that Curiosity would develop? Well, all of that, every single one of these events, that takes place in a very narrow range. This tiny little envelope here, this little box, bounded by about Mach 1.5 and 20 kilometers or so. None of this is of any help if you can't reach this box. And a vehicle like the Apollo capsule could never reach this box, no matter how it flew. So the central challenge that we are trying to address is, how do we take a vehicle with a large ballistic coefficient and enable it to pass through the high energy phase in such a way that it reaches this box where terminal guidance strategies can be employed, like parachutes, without impacting the ground first? That's the central problem that we're trying to address, because closing that gap is absolutely essential if we want to land human beings on Mars. Now, one potential way to do this, which NASA has been looking into and has put a great deal of confidence in, is the idea of an inflatable aerodynamic decelerator, an IAD. And the idea of this is you drastically increase the area of the vehicle without significantly increasing the mass, because inflatables don't have much of a mass penalty associated with them. That lowers the ballistic coefficient by a huge amount, and the result is a lower terminal velocity and a safe entry to the envelope where technologies like parachutes can be employed. So this is some flight video from the last flight of the large low-density supersonic decelerator. You can see the inflatable deploys very rapidly, very suddenly. It's a very quick configuration. There's no chance for the vehicle to go unstable. However, the thing I really want you to notice is what happens after this. After the deployable was safely deployed and the test is success, it tried to decelerate using a conventional parachute, which is very similar to the ones that Viking employed when they landed on Mars. Now, right now, it's flying through conditions very similar to what was experienced on Mars, and that happens. The parachute completely shreds. That is what is expected to happen if we try to use a parachute in the regime that this vehicle was flying through, which was not terribly fast. This is about Mach 4. And the reason it shred was because the parachute was sitting in the vortex wake of the capsule itself. But that's something that's going to happen on Mars as well. So you can't simply, the takeaway from that is you can decrease the ballistic coefficient effectively, but you have to reach that parachute deployment envelope if you want the vehicle to land successfully. There's really no way around that. Larger parachutes don't help. there is really no way to make a parachute that can deploy in that safe, outside that safe envelope as far as we know. Now the second method, which is the method I'm going to be focusing mainly on today, is the concept of supersonic retropropulsion, SRP. And the principle involved in that is we ignite the retropropulsive system which the spacecraft has while it is still traveling supersonically. Now, most vehicles that have gone to Mars, this includes both the Vikings, this includes Phoenix, and Polar Lander, all had some type of retropropulsive system for use in the terminal phase. They all used a small bank of engines to get rid of their last 100 or 200 or so meters per second of velocity. And the idea of supersonic retropropulsion is, well, why don't we simply turn our engines on much earlier in the flight when we're still flying in the hypersonic regime? Now, there are obvious downsides to that. The first one of those is you need more propellant. So unlike IADS, there's a significant mass penalty associated with this strategy, which is why it hasn't received quite as much attention as IADS from NASA. But there's also the problem of it doesn't actually change your ballistic coefficient. So if you turn the engines off, you will start falling at a faster velocity again. It doesn't permanently decelerate you. It only decelerates you as long as your engines are firing. In fact, the penalties associated with this extra propellant are so bad that if you actually do some mass trade studies, the result is that inflatable aerodynamic decelerators get you about twice the effective payload on the surface as a supersonic retropropulsive system does. So these two charts show the payload mass fraction, so that's higher is desirable in this case, and the total payload mass versus the total spacecraft mass for IADS of 3 different diameters, and the purple triangles for supersonic retropropulsion. So you can see supersonic retropropulsion only gets us about half the effective payload to the surface when compared to IADS, no matter what the mass of the vehicle is. Same thing for the payload mass fraction. So just basically looking at this, it seems pretty obvious that IADS would be the solution that we want. They are more effective at decelerating the vehicle. They're more mass effective. And so in light of this, why would we even consider something like SRP? And the answer has to do with control authority. IADS are purely aerodynamic methods of control, which means they're only effective when the dynamic pressure on them is above a certain threshold. Now, a vehicle going through an EDL process follows the same trend as a vehicle in a launch phase does, where there's a period of maximum dynamic pressure and a region around it where there is significant dynamic pressure on the vehicle. Before that, it's too high up and the air is too thin, and after it, it's going too slowly. So an IAD, even if it would be effective at decelerating the vehicle, is only useful within this narrow velocity envelope, which you can see is only about this is the pressure profile of the Mars Science Laboratory. Is only effective within the first 50% so of the trajectory. After that, if you want to perform a divert maneuver, if you want to change landing sites at the last minute, if you find you're way off target and need to make a turn back toward the target, you don't have that choice. An IAD does not give you the control authority necessary, in order to make that necessary correction. So the answer, why would we use SRP when the vehicle, when it's clearly an inferior means of mass performance, is because precision control and landing is absolutely essential for every architecture that NASA has studied for humans on Mars. Not just because greater control authority is necessary for improved safety, reliability, and possible abort modes, but also because it is pretty much every architecture that NASA has studied requires landing near pre-deployed assets. Very few feasible architectures have been proposed that can land everything in a single one-up spacecraft. Those are typically way too expensive and way too heavy to launch from Earth. You have to land your mission in individual modules, which means you have to be able to land it precisely next to the pre-deployed assets. And that is what necessitates the use of something like SRP. That is why IADs, even if they're more mass effective, are not considered to be the best long-term solution for a human architecture to Mars. So let's take a look at SRP and what it entails and why some of the problems and why some of the aspects of it are so hard to overcome. The best way to parameterize SRP is by this parameter called the thrust coefficient. Now, if anyone has a propulsion background in here, this is not the thrust coefficient for an engine nozzle that you're principally familiar with. This is a force coefficient. It's in every way analogous to lift coefficient and drag coefficient is to lift and drag force. The force of relevance, though, is simply the total force on the vehicle due to the thrusters. And then you just have the dynamic pressure in the relevant area of the vehicle. So supersonic retropropulsion works, the manner in which it works depends pretty much entirely on what the value of the thrust coefficient is. So you can control thrust coefficient by either flying at a different altitude, at a different dynamic pressure, or changing the thrust levels. You have a great deal of control over it. And the principal idea is if you, what was initially discovered about SRP way back in the 1960s was if you have a vehicle which is blunted and has a bow shock set up in front of it, putting an engine on the nose and firing it at a very low thrust coefficient, like maybe 0.1 or between 0 and 0.1 or so, displaces the bow shock from the surface and redirects the heat load away from the vehicle. So this was the original idea of using SRP, was as a means to modulate the drag of vehicles that didn't have the mechanism to undergo a configuration change, like aerodynamic control surfaces or flaps or anything like that. So you increase the thrust coefficient, you displace the bow shock, you decrease the drag, and that decreases the total axial force on the vehicle. So even though the engine is firing retropropulsively, even though it's trying to slow you down, the total net deceleration is actually decreased, because the thruster is actually having a greater penalty on the drag. It's actually reducing drag more than it is itself decelerating the vehicle. And that was the key discovery that got people interested in SRP. A couple years later, though, they made an even more interesting discovery, which was that if you orient the engines correctly, you can actually preserve the drag. So the method I was just speaking about here, if you look at this plot of thrust coefficient, so that you can think of this as the extent, since this is a constant dynamic pressure, you can think of this as the total thrust the vehicle is exerting, versus the total deceleration force. This curve right here was the original discovery of SRP. Vehicle has some certain drag coefficient. As soon as the engines fire and disrupt the bow shock, however, that drag basically disappears, and the vehicle starts behaving as if the only force acting on it is this unity line, where there is purely decelerative thrust acting on the vehicle. So that's what this curve right here is. But what was eventually discovered was if you place the engines not in the axis of the vehicle, but around the periphery of the vehicle, you actually you do not disrupt the bow shock. You enlarge the bow shock. And the result is a preservation of drag up to a very large thrust coefficient, almost as high as 1 in this case. So if you were to thrust at CT1 in this situation, you wouldn't just be getting the deceleration due to the engine, you'd also be getting deceleration due to the preservation of drag. So that's very beneficial. You're getting twice the effective performance out of your engine. Now the original purpose of this was to be applied to Viking. This sphere cone right here is designed on the Viking concept because they thought this might be a useful idea for Viking. Unfortunately, it never ended up getting used on Viking. As I mentioned, Viking did employ retropropulsion, but only in the final terminal phase. Before that, it used a conventional, like every other vehicle that's landed on Mars, used a conventional disc band gap parachute and an aeroshell. So this never saw a flight concept on a Mars lander, and it kind of fell out of interest during the 80s and the early part of the shuttle era. But then about 15 years ago, the idea became interesting again when Mars started to be all the hype. And people started performing modern CFD validation work on the wind tunnel studies that had been done all through the 60s and 70s. And that is pretty much what most of the modern focus on SRP has been. It's been on reproducing the wind tunnel results from the original 1960s and 70s work. And we've done a pretty good job at it so far. We've generated CFD models which agree with the wind tunnel data, plus or minus 10 to 20%, which is pretty good for a phenomena like this where there is reacting flow, a need for species analysis, fully hypersonic. So for a system like that, that's pretty good agreement with modern CFD. So what the modern CFD research has validated was the original discovery of the original wind tunnel studies, which is there is a range in which, for a peripheral geometry, so where your engines are oriented around the periphery of the leading edge of the vehicle, there is a range of CT where drag preservation is relevant. Outside that range, it's fair to treat the vehicle as being in a purely aerodynamic regime because the thrust is so low, or a purely propulsive regime because the thrust is completely negating all aerodynamic effects. Within this region, though, there is the chance of using both, of having both forces exerting relevant amounts of acceleration on the vehicle. And a convenient way to think about this was proposed by Dr. Corzon and Dr. Braun, which is in terms of a drag preservation envelope, so a flight envelope in which drag preservation is still somewhat relevant. So if you assume an exponential atmospheric structure at a scale height of h, we can we can redefine the thrust coefficient in terms of vehicle properties and atmospheric properties, reshaping that and solving it for h in terms of v, so in altitude velocity space. That generates an envelope within which drag preservation is said to be relevant. Now that's not to say SRP can only be used in this envelope. SRP can be used, like I said, at any point, any altitude, any velocity. That's what makes it so useful as a control scheme. But within this envelope, set by the maximum and minimum thrust coefficients where drag preservation is said to be relevant, set with a floor defined by as close as you're willing to get to the terrain, and a maximum velocity set by the maximum Mach number that the vehicle is willing to ignite the engines at, or a couple other factors which I'll get into. Within this envelope, there is the possibility of employing drag-augmented thrusting. And as you saw in the previous plot, that can get you almost twice the effective deceleration out of your engine. So you're saving a significant amount of propellant if you're willing to work like that. So this actually received its first flight test just last year with SpaceX CRS-4 launch. So again, as I'm sure you know, SpaceX has been designing the first stage of its Falcon 9 vehicle for reusability, which means it has to employ a supersonic retropropulsive burn to arrest its downrange velocity, come to a stop, descend, and then perform a targeted landing, hopefully back at the launch site someday. And there was a chase plane on the CRS-4 flight which managed to capture exactly this phenomena for the first time in an actual flight condition. So this is the first stage coming back. I don't know if you can see this. This is it igniting for its downrange control burn. It's still in a regime which is high enough that it's effectively a vacuum. As it descends, however, you can see this bow shock forms. Now watch what happens when the engine shuts down. See that? The bow shock, which was originally displaced, drops and comes closer to the vehicle. So that's exactly the phenomenon which was predicted by the wind tunnel experiments. And this was the first time that it was actually seen in an effective flight condition. Now, eventually the vehicle passes through regimes where it's effectively flying through, no longer in that SRP envelope, but still this was the first effective discovery of, or the validation of the wind tunnel and CFD results in an actual flight condition. So, at high thrust, we should ask the question, at high thrust we know drag is effectively turned off. Why didn't we use that? After all, we solved that problem for the moon. Does that mean we can simply land on Mars by employing high enough thrust that we don't need to worry about aerodynamic loading? The answer to that is yes. If you're thinking that the answer to that is yes. However, a fully propulsive architecture landing on Mars would require an enormous launch mass. Just to land one equivalent lunar module on the surface of Mars would take two SLS Block 2 launches, because a fully propulsive descent architecture requires multiple refuelings, both in low Earth orbit and in Mars orbit, which requires a higher launch mass. So I want to be absolutely clear. SRP is not properly thought of as a fully propulsive descent architecture. You can thrust at high enough thrust coefficients that you can consider it fully propulsive, but if you are doing that, you are throwing away some perspective gains. And that's what I'm going to be looking at. I'm going to be looking at where between the fully aerodynamic architectures and this fully propulsive architecture can we get the most out of this drag augmentation phenomena and minimize the amount of propellant required in order to land a human-sized vehicle on Mars. So our overall goals are, let's look at these phenomena quantitatively and decide and figure out exactly how much of a benefit can this technique give us. Is it a significant amount of propellant savings that it's worth pursuing? Because there obviously will be trade-offs associated with this. So these are the questions that my study is aiming to answer. So first to do this, we need a reference spacecraft. And the reference spacecraft that we're designing is something like a transit vehicle that will transfer astronauts from Mars Transit Hab, so something that takes them from Earth to Mars, down to the surface. Possibly employing aerobraking, which means it should have enough endurance for at least a couple of days while the aerobraking process is in progress. And conveniently, the Orion crew module actually meets those requirements pretty nicely, and it has the advantage of having published hypersonic aerodynamic data that is available and open to the public. So the reference vehicle we're going to be designing here is effectively an Orion vehicle, except we will be adding hypergolic engines that give it enough oomph to function as a proper SRP vehicle. Orion has a reaction control system, but it's not designed for fully propulsive landings. That's not its purpose. Still, it's a very useful reference vehicle for us to use for this purpose. So this is going to be our reference vehicle. It's an Orion vehicle with an L over D of about 0.65, assuming unconstrained angle of attack modulation, with 10 tons wet mass. Now, dry mass is not specified in this architecture. The vehicle is assumed to consume as much propellant as it needs in order to touch down. And then the goal is just to report back at whatever, I'm sorry, it looks like my slides are cutting off some of this here. And the goal is just to report how much propellant is required in order to affect the touchdown. So, how do we parameterize our drag preservation model? When we're flying through the SRP envelope, how do we decide how much drag is being preserved? The way we will do so is with this function, the preservation function, which describes how much aerodynamics are still functioning as a function of the thrust coefficient. The conventional way this has been assumed in the literature is with a piecewise fit through every single CFD point. That's how sparse the CFD data is. It's sparse enough that you can still do that from a design perspective. But we're going to fit a nice smooth function to it here. Something that has some useful parameters for a design engineer. So, for example, in this case, we can parameterize this curve entirely by two useful design parameters: the thrust coefficient at which 50% of your drag is still preserved, and the rate of drag disruption onset at that 50% point. So this model we'll apply it to a couple of wind tunnel points, then we'll interpolate to get our reference vehicle. This is CFD data performed by Bakhtian and Aftomosis. And then the dotted lines show my best fit of this design model as a function of different nozzle geometry. So what this is showing is showing different cant angles, so different divergences of the nozzles on the leading edge of the vehicle, as well as different radial spacings around the vehicle itself. So the engines themselves can be located either exactly at the center, where you get almost no drag preservation, or they can be moved to the periphery, where they are providing full drag augmentation, and they can be canted out, where they are enlarging the shock a great deal, or straightforward, where they're augmenting it very little. And it turns out this drag preservation model is a reasonably good fit for the wind tunnel data we've got at hand. Obviously, it's not perfect. More wind tunnel data would give us a better drag fit, but it's what we got. So looking again at the drag preservation envelope and this parameterized drag preservation function, we can calculate what the optimal CT is going to be whenever we are inside the SRP envelope, and that will give us a command that'll give us the command that the controller needs to follow for the thrust coefficient. So it'll tell us at what value we need to operate the throttle. So this again is the total axial coefficient on the vehicle, which is a combination of thrust and degraded drag. We simply take the derivative with respect to thrust coefficient, find the zero, and we get this nice analytical function, which is a function of the two design parameters, CD50 and D, and returns the optimal throttle control value. All right, now let's take a look at the equations of motion. Now, I don't want to rush through this. I really hate it when someone just throws up a page of math and says, here it is, but I do think there is some utility to be had, though, in going through the 3D equations of motion, which is what this what the simulation was run in. So you're probably familiar with these familiar equations of flight. These are two-dimensional, constrained to a plane, assuming the planet is flat. You're probably familiar with all of these terms. However, what if we want if we're going to move the model to a three-dimensional system, where there is now out-of-plane motions and the planet itself is rotating, which is how this model is going to be set up. It's pretty easy to understand how we modify the equations. So we'll take our familiar two-dimensional equations of motion, which are governed by aerodynamics and gravity. We will add in the centrifugal factor of the vehicle's motion to account for the circularity of the planet. There's Coriolis acceleration due to the rotation of the planet, and there's also centrifugal factors due to the rotation of the planet itself. So you're probably familiar with this much of the equations of motion for a re-entering vehicle, or indeed any flying aircraft. You simply add in these terms where phi is the latitude, theta is the longitude, and psi is your heading. Where the third degree of freedom, our heading itself, is given by this equation shown here, which is also governed only by the aerodynamics, the centrifugal forces, and the Coriolis accelerations, plus the planet's rotation. The kinematics transform from 2D to 3D very simply. We just change our altitude equation to our radius equation, and then the downrange equation via spherical trigonometry gives us 3 kinematic equations for our downrange distance, for our downrange velocity, our eastward velocity, and our northward velocity. Then finally, we need to incorporate the factors of thrust. Those equations we just derived were for purely aerodynamic vehicles. If we include thrusting effects, it's actually very simple. We simply modify the aerodynamic quantities of lift and drag as shown previously with the augmented functions in terms of thrust and thrust angle. So turning our drag and lift forces into axial and normal forces, which are combinations of aerodynamic and thrusting loads, plus the rocket equation telling us how the mass of the vehicle is changing, gives us our actual equations of motion. So I know I could have just thrown this up there and you probably all would have believed me, but I do think there is value in seeing where these equations come from. So these are the equations that the vehicle is going to be operating under its full 3-dimensional equations for the simulation. Now let's take a look at the environment that the vehicle is going to be attempting to be landing in. So this is the comparison of the atmosphere of Mars versus the atmosphere of Earth, shown on the same scale as its true vertical terrain relief. Joel, can I ask you to turn off one of the light switches? Just,
how about this?
yeah, there you go. We can turn that back on once we get away from the slides. So this just shows the atmospheric structure of Mars that the vehicle is going to be operating in. This is a latitudinal cut through the largest terrain feature. This also highlights one of the problems of Mars EDL, which is Mars has a much higher terrain relief than Earth does, which is why most of the Mars spacecraft that you're familiar with have landed in the northern hemisphere. It's because the atmosphere is so much significantly thicker than it is in the southern hemisphere. So this is the atmosphere that the vehicle is going to be operating in. We'll build a model out of it. You can turn the light back on. It'll be a simple exponential function of altitude, 2-piece linear temperature fit, with these atmospheric parameters assumed from a combination of Viking and Pathfinder data. Now it's important to note that the biggest uncertainty in pretty much any Mars EDL trajectory simulation is the atmospheric density. Mars has horrible variation in terms of its atmosphere. It can be as much as 20% from day to day. This is what we call a tornado plot of the density variation from the nominal up to 100% variation high and 100% variation low as a function of altitude generated with a numerical model called MarsGram. So you can just see the day-to-day variation is really quite high. For time reasons, I can't go into why this isn't simulating that, but atmospheric density is the principal uncertainty which this simulation is going to need to address. The planet itself, like I said, is simulated as spherical with terrain factors given from the Mars Orbital Laser Altimeter, shown here. The gravity model, however, is a simple point mass model. There is no geodesy used here. It was available in MATLAB, but it does horrible things to the runtime, so I decided not to use it because geodesy effects just don't matter over 300 to 500 seconds that EDL is taking place. All right, now let's take a look at the controller logic that the vehicle is implementing here. So the vehicle flies through a series of linear states through which there is a gate at which the vehicle senses in order to pass to the next state. It's somewhat more easy to... So the vehicle initializes in a Keplerian state outside the atmosphere. For the moment, it's been given identical flight states to MSL. So it has the exact same entry conditions as were given on MSL. It flies until it detects that it has encountered the atmosphere, which is defined by a 5% of an Earth G acceleration. Then it trips into a fully ballistic phase of flight. Once the ballistic phase detects that it has encountered a G limit or a heating limit violation, if that occurs, the vehicle throws a warning and tries flying again at a slightly lower velocity. Really none of that is terribly important in this case because all SRP factors take place long after peak heating and peak G loading have occurred. So I'll skip ahead a couple of phases. The vehicle then, once it is able to pass through the peak limits, it tries to level out at a pre-specified altitude, which is defined as the altitude at which the vehicle is going to enter the SRP envelope. And that is our main design variable. We vary the altitude at which the SRP is initiated and investigate the final propellant mass fraction that results after the vehicle has passed through SRP and executed a descent to the ground. So that's what each one of these following states is. Now the color coding carries through to each one of these states. This is Gale Crater. Actually, can you translate it? This is Gale Crater, the target, the landing site for MSL, flown with a vehicle, flown with the reference vehicle shown here with a lift over drag of 0.65, as well as a couple of other different perspective L over Ds. Now, the color coding carries over from the previous slide. So the red is shown as the pull-up maneuver. This is the vehicle transitioning from a fully ballistic phase to level flight. Once it's in level flight, which is the yellow phase right here, green is shown as the transition just when the vehicle is entering SRP, and then blue is actual burning within the SRP envelope. So you can see the general trend here. At higher altitudes, the vehicle spends a greater amount of distance, the vehicle traverses a greater linear distance within the SRP envelope. So that means it's decelerating slower, right? Because the SRP envelope isn't a geometric envelope, it's an energy envelope. So the vehicle tends to spend more time in the SRP envelope at higher altitudes, and therefore capitalize a little bit more on the loss of on the preservation of drag. However, it also means that it is accumulating more gravity losses. Now, gravity losses, if you remember, are the wasting of delta V capacity in order to keep the vehicle from falling under the influence of gravity. So since the vehicle is flying through the SRP envelope horizontally, it means the longer it spends in the SRP envelope, the greater gravity losses it accumulates. So there is a trade-off there. But these four perspective lift over drag ratios, flown at a wide span of altitudes and then down to the surface and investigating what the final PMF was, allows us to perform our first design analysis of this concept. So here are the same trajectories shown in 2D. You can see how the envelope changes as the vehicle flies with different L over Ds. Now, again, the reason the envelope changes is because the vehicle has absolutely no reason to engage its propulsion systems if it's still capable of level flight. That's important to understand. Stall velocity in this setup runs along a contour, a dynamic pressure contour, parallel to the SRP envelope. So when the vehicle is capable of a much higher L over D, it means it has a much lower stall speed. So some of the SRP envelope is eaten up because the vehicle is still capable of level flight. There's no reason for the vehicle to utilize its propulsion systems when it's still capable of flying level. So that's why the envelope tends to grow as L over D gets smaller here. But you can see you can see how the vehicle spends a greater period of a greater total velocity distance within the SRP envelope at a low L over D. So let's take every PMF from this and let's put a design study together out of it. So this is the first critical result to answer the main question that we had, which is how much propellant are we saving by employing this optimal SRP strategy compared to the simple approach where we just brute force our way through the SRP envelope, thrusting at the maximum thrust to weight ratio that is safe without violating the G loading constraints on the vehicle itself. So shown in gold is the optimal SRP, and then in gray is the conventional SRP. And you can see for a given SRP envelope altitude, say 5 kilometers, we are saving almost 5% in propellant. So for our current reference vehicle of 10 tons, that's 500 kilograms of propellant saved right there. And you can see that's also not a terribly sensitive function of altitude. That's across the altitude range. So the answer to our first question is how much propellant are we saving by employing this maximum drag preservation on the SRP envelope? It's 5%, quite a lot, comparatively speaking. But of course, the question is how much of that propellant have we lost as a result of maintaining level flight when we could have been descending? And it turns out that the answer is not much. The gravity losses incurred are only on the order of 30 to 50 meters per second. Now, remember, the vehicle itself is undergoing a total deceleration of over 1.4 kilometers per second, so 1,400 meters per second. So losing this much is not terribly significant. This is the finding that surprised me the most. I really expected gravity losses would be very significant to the vehicle, and cause there to be some boundary to where this trade-off is no longer useful. But the answer is, it actually turns out to be, we haven't uncovered where that edge is yet, where gravity losses become so significant that there is no reason to continue using this SRP system. Now let's look at what L over D does for the total propellant mass fraction. Now we didn't just pick those L over Ds arbitrarily. The L over Ds that we picked were meant to represent an unconstrained L over D for Orion if it is free to adopt any orientation it wants, which it can if it has these SRP systems. There's also Orion as it conventionally stands with a CG offset maximum L over D. Then Apollo and MSL with an L over D of about 0.35 and 0.25, as shown right here. So you can see high L over D for a constant aerodynamic, high L over D for a given propellant mass fraction has an interesting effect not just on the altitude at which you pull up at, but also on the total downrange effectiveness that you're able to get out of the control system. Now this is, remember, was the key reason why we cared about SRP as a useful system. SRP was not supposed to give us superior mass performance, and indeed it didn't. But what SRP was supposed to do was enable us to have a great amount of control authority over the downrange and potentially the cross-range divert maneuvers if they were necessary to perform. And you can see here the total downrange the vehicle travels as a function of the L over D that the vehicle has. And you can see we're getting, for say our conventional Orion vehicle at about let's say 50% propellant mass fraction, we're getting over 120 kilometers of downrange actuation. That's huge. That's the entire width of the Viking of the Viking landing ellipse. MSL itself had a landing ellipse that was only about 10 kilometers wide. So what this is showing us is that even for a very low L over D like MSL, the propellant penalty is indeed quite high, but the downrange control authority that you get as a result of that setup is actually incredibly large. So this has kind of demonstrated what we expected about the trade-offs, and that's a useful method of validating the studies. Now, what do we lose? There's obviously you never get something for anything in this field, and it turns out what we are it turns out what we are losing does again come down to the propellant mass fraction. There are regimes where the vehicle has no achievable solution, has no non-zero payload mass, has no payload mass fraction that is less than 1, or less than 100%. Now, part of this, what this plot is showing, part of this is an artifact of my code, I think, and it has to do with the fact that the vehicle is not performing any, that the controller is not performing any truly robust optimization. There is no contour following, for example. The vehicle never follows a max G load contour, for example, and as a result, its control options are somewhat limited for deciding when it is going to initiate its pull-up maneuver and adopt the level glide phase. So without some additional heavy optimization, I can't be quite sure that this boundary is indeed a real artifact, and that you couldn't extend it a little bit further. But what I'm seeing currently with my code is there are regions as we expected where no solution is possible. So where do we go from here? Like I said, the solution has only been softly optimized. Again, there is no optimization code running here in the usual sense that we refer to optimization in our department. There's no GPOPs, no co-states, no Hamiltonian, none of that so far. This is purely soft optimization taken from the insights of the nature of SRP. However, I definitely think that hard optimization would provide real benefits for it, because again, the control logic that you saw was designed by us. It was designed by humans. There's no reason it is necessarily going to be the true optimal strategy. So I'm hoping in the near future we can get a chance to employ some of the hard numeric optimization methods like GPOPs or particle swarm, which will give us a more robust control law, which the vehicle can then use. Finally, another thing which we're very interested in working on in the future is this controller is constraining itself to level flight within the SRP envelope. And again, the reason for that was because it seemed obvious that level flight was the way to minimize gravity losses. But given how fantastically small the gravity losses ended up being, this is kind of suggesting that maybe there is an argument for looking at other flight regimes through the SRP envelope. The one we're really excited to look at is if the vehicle, instead of passing through the SRP envelope like this, enters with a negative flight path angle and spends literally the maximum amount of time possible in the SRP envelope, only exiting when it gets close to the terrain, there will be the flight path angle will be higher, so the gravity losses will be higher, but the amount of time spent in the SRP envelope will also be higher, so the amount of aerodynamic deceleration that you can capitalize on will also be higher. So whether that's a trade-off that's necessary to be made, I'm quite interested in seeing. And finally, the model that I discussed about drag preservation is only designed to work if your engines are located on the leading edge of the vehicle, on the forebody. If your vehicle gets big, though, something like the 100 metric ton class lander that the GRA-5 might have been looking at, for example, there is another option which is available. If the engines are recessed away from the leading edge of the vehicle, if they're moved back to the aft body of the vehicle, it's possible to almost completely decouple thrusting effects from aerodynamic effects again. So the preservation function becomes almost a flat line. You get almost full drag preservation way up to thrust coefficient of 20. This is some CFD work which was performed by Chris Cordell at Georgia Tech, which first uncovered this idea. This has limited application to a small lander like our reference vehicle, only 10 metric tons, because the vehicle simply isn't large enough to have that kind of recessing of its engines. But for a larger vehicle where there can be actual displacement between the engines and the vehicle forebody, there is real benefits to be had here. So what this effectively does is it enlarges the SRP envelope well up to, say, the Mach 10 or Mach 20 region. So this is something which I'd like to look at in the near future as well, because it has applications to slightly larger vehicles. If you'd like some more information, I took some of the primary sources that I cited the most here. Beyond that, though, thank you for listening. If you have any questions, I'd be happy to take them at this point, and here's all.
Thank you.
John, take it away.
All right, any questions from the general audience?
Max, what in the payload obviously takes into account leaving Mars. I mean, what thrusters were you going to have on there to come home?
So I mentioned how most architectures look at using a very modular, very specialized approach. So in this case, the answer is actually no. The vehicle that lands you on Mars is probably not going to be the vehicle that takes off from Mars. And the reason for that has to do with the type of propulsion system that's really optimized for that. For a vehicle that's going to land on Mars, it's likely going to spend a long time beforehand in interplanetary space, and the storage of cryogenic propellants in interplanetary space for a long period of time is a very hard problem. So a vehicle that lands on Mars, at least until we're advanced enough to have propellant depots in orbit around Mars, landing vehicles are probably going to employ propellant that can be stored for a long period of time, like hypergolics and monopropellants, for example. A vehicle that launches from Mars, on the other hand, has the opportunity to utilize in situ resource utilization refueling. So a vehicle that launches from Mars is overwhelmingly likely, actually in the near future, to probably employ a LOX methane type architecture, which has a higher specific performance than hypergolics. So in this case, the answer is the functions of takeoff and descent will probably be performed by two entirely separate vehicles.
Gotcha. Okay.
Did you do any analysis to try to figure out how much of that payload you bought back by being able to do this that you had a chart early on that showed the overall payload difference between aero brake
Yeah.
and what I call aero brake and the retropropulsion. Did you do any numbers to see how much you might have bought some of that back?
You're talking about this one right here?
Yep.
So again, getting 5% PMF back was what I was typically seeing. So you could shift this line here up 5% or so. Oh, so sorry, this line right here. This line up 5%. So from 25% to say 30%, from 25% to 30, from 20% to 25% or so. That's about the shift that you can get. Now it's never going to be higher than IADs. I mean, the notion that you could make an engine or a fuel tank lighter than an inflatable element is just kind of ridiculous. So again, the goal is not to get superior performance to IADs. The goal is to get superior control and as good PMF as possible.
If not, then I'll ask the general audience to leave. Tell me how much you're coming.